the roots of your characteristic equation will be your eigenvalues. Yeah, that's what I was wanting to say. So we need to FOIL this out. I think this is going to be 3 minus 4 lambda plus lambda squared. Oh, I hope I don't get imaginary numbers. So lambda squared minus 4. What? Minus 1? Oh, lambda. Minus 1. Okay. It's what? All right, so yeah. This is what happens when you make problems up. Okay, so lambda is equal to -4 or -4 plus or minus the square root of 16 minus 4 divided by 2. So can we factor out a 4 from under a square root? Then we get 3, so 2 root 3. Cancel out with a 2. So we got 2 plus or minus root 3. Is that right? So not very nice looking. So in any case, if we set up our diagonal matrix, well, we can find our eigenvectors for each eigenvalue by finding the solution to the null space when we put the specific lambda in. So let's take lambda equal to this for now. Let's do this in a different color. Lambda is equal to 2 plus square root of 3, and then we'll, pardon me? That's not always positive. Yeah. Wow, which one? Oh yeah, there's 2 lambdas, but we're gonna find each of them for each lambda. These are absolute value or determinant brackets because I want to find the determinant of that. Forget I said absolute value. Determinant. Yeah. So remember, straight line is for, it means you're going to take the determinant of that. All right. So, oh, this is going to be ugly. So A minus lambda I is your matrix. So 1 minus lambda, so that's 2 minus root 3. I guess put a plus there for now. 2, 2, and then 3 minus lambda. Oops, lambda is equal to 2 plus root 3. And this is going to give us -1. Minus root 3. 2, 2, and then this is going to give us +1 minus root 3. Did I do that right? Yeah. So if I want to row reduce this, this is going to be kind of weird, but I have to multiply the top by something. Multiply row 1 by negative. That's already negative. So 2 over 1 plus root 3 R1 plus R2. Minus 1 minus root 3, 2. So this is going to give us 0. And yeah, the other one should be a 0 too. It's not 0, is it? It'll be 4 divided by that. And then you have to add. Oh, it's going to be 0. Let me just double check. So this is just a simple algebra thing. 2 divided by, what is it? 1 plus square root of 3 times 2. And then I want to add it to 1 minus square root of 3. Wait. Oh, thanks. Out. It's supposed to be 0. Negative square root of 3 minus 1. Yeah, same. All right, let's go back and check our eigenvalues. Yeah. All right, well, let me just check the eigen. I'll still take your example, though. You think so? Yeah, I just changed the problem. Chris? Okay. So, all right, let's get this fixed up. So I troubleshoot, I just asked Chris how to do it. All right, so we went wrong over here somewhere. Oh, this is a plus. So that's 20 instead of 12. So this is a 5. So that's it, right? All right, so back on the game. We got lambda is equal to, let's take one of those and then try to find its eigen, yeah. Is that, wouldn't that be the same? So the 2 is negative?
That is totally different from 2 plus minus root 5.
So yeah, what I'm hearing, according to this should be a plus here. So the sign of the 2 doesn't change, right? Yeah, I think this is correct. Let's go with this and see what happens. All right, we have a minus lambda I is equal to 1 minus 2 plus root 5 with parentheses. We have 2, 2, and 3 minus 2 plus root 5. And then again, if we simplify this, this is negative 1 minus root 5, 2, 2, and then this is positive 1 minus root 5. So this is where we do that funny thing where we have to multiply by 2 divided by 1 plus root 5 times R1 plus, and then add it to R2 so that our first row will remain the same. And then our second row will be zeros. So what I'd like to check is maybe I'll check 2 plus 1 plus root 5 and add it, multiply it to 2 and then add it to this and see if it comes out the way it's supposed to. So this is just, again, some algebra. We got 2 divided by 1 plus square root of 5. Times 2. And then we want to add it to the bottom row in the second column. And that would be 1 minus square root of 5. And hopefully this is equal to 0. Oh, yeah, it's equal to 0. So the point is that when you're doing this, and if you've done this correctly, you're going to have at least one row of zeros because you're going to get something in the null set. The null set is not going to be just the 0 vector. So we're going to get a vector out of this. And the solutions for this would be x2 would be free. And so x1 would equal to negative 2 x2 divided by negative 1 minus root 5. Something like that. X2. So let's try that again. So this would be 2 divided by 1 plus root 5 and 1. So that can serve as your basis or your oh, it's good. You catch those mistakes. So this would serve as a basis for the eigenspace that spans the eigenspace for this particular eigenvalue. So in other words, we have an eigenvalue, e-value of 2, let's call it lambda 1, is equal to 2 plus root 5. And then our corresponding eigenvector, let's call it v1, is going to be this, 2 divided by 1 plus root 5 and 1. Okay? We do. Oh no, because it's a dummy variable parameter. All right. Now we would do the same thing for our other e value. Um, so since I'm out of space, can I just say your other eigenvalue is 2 minus square root of 5, and then your eigenvector, oh, I erased it. Wonder if I can get the last command. So the eigenvalue for the first one, lambda 1, has this. The eigenvalue for the second one has a negative. So it's close to this, except they're both negatives. Wait, this is a positive. Well, you can do whatever you want. This Wolfram Alpha, the program actually rationalized the denominator, and so that's why it looks different from what we have. So I'll just take their copy. Actually, I just take a picture of their copy. And so this is their vectors. They wrote the vectors as row vectors. Rationalize. No. So in the exam, I do the problems, and then as I write the problems, I usually have Mathematica open and I check the work, and then yeah, yeah. So if you start getting weird eigenvalues and eigenvectors like this, then you probably want to go back, and we're going to try to have nice numbers. Not yet, maybe. All right. So we're going to assume that this is rationalized. So that doesn't leave us much room for our final conclusion here. The whole point in doing this is to come up with a matrix P and the matrix D. So I'm going to write it small, and then we'll do another example where we have nicer numbers. So our A matrix here is actually equal to, do they put P inverse first or P first? P first. So P, D, P inverse, where D, that's the easy one, is equal to the diagonals, and the diagonals is just lambda 1 and lambda 2. So that's 2 plus root 5, 0, 0, and 2 minus root 5. And then your P matrix. So by the way, these two vectors, as vectors, are linearly independent from each other. And the fact that they're linearly independent from each other means that we can put them as columns in a matrix, and then they will be invertible. And so the column matrices are going to look like 1. Oh, they also have to be in the same column as the eigenvalue in the D matrix. So my D matrix has an eigenvalue of 2 plus root 5. And so my first column for my P matrix needs to be the corresponding eigenvector. So that would be 1/2 minus 1 plus root 5, comma 1. And then their V2 matrix is the eigenvector for the eigenvalue 2 minus root 5. And so that will be 1/2 minus 1 plus root 5. And then the second component is going to be 1. All right. Well, that sucks. That was a lot of work. If you want to check to make sure it works, you're trying to get your D and your P. We should do one more example with nicer numbers. What? Yeah, you can do AP is equal to PD. So if you want to show that they're equal, instead of looking for the inverse, you can just multiply both sides on the right by P. So AP equals PD, and then show that those two things are equal. But really, you should find the inverse. But we're not going to worry about that. Okay, let's do another example with the 3x3 and hopefully a nicer. Do you have a nice one? All right, so let's move on. Example. All right, what is it? 1, 3, 3. -3, -5, -3. 3, 3, 1. All right. So this doesn't look that easy. All right. So let's do this example, and let's go through the process of. Maybe I should tell you what the process was. Find the eigenvalues, find the eigenvectors that are linearly independent, form the matrix P, and form the matrix D. Okay, so I'll put this step-by-step process at the end after we do it. So let's find the eigenvalues. And remember, you find the eigenvalues by setting up your determinant. So I'll use a straight line minus lambda I. And so that's 1 minus lambda. So the diagonals are essentially going to have a minus lambda, and everything else will remain the same. So I've got -5 minus lambda for the 2, 2 slot, and then 1 minus lambda for the 3, 3 slot. And let's let's multiply it all out, find the determinant any way you want. So I'm going to find it the long way, 1 minus lambda. And then the submatrix is -5 minus lambda, -3, 3, 1 minus lambda. And then the next term will be negative. I'm expanding on the first row. And then I have a -3, -3, 3, 1 minus lambda. And then the last term would be a +3, expanding on the last column in the first row. And I have a -3, -5 minus lambda, a 3 and a 3. So I got 1 minus lambda, and then I have a -5 minus lambda, 1 minus lambda, minus -3, call it a +9. And then I have a 3 times -3 times 1 minus lambda, minus -3 again, so that's another +9. Plus 3 times, this is a -9, minus 3 times -5 minus, oh, out of space. All right, well, I don't know. I'm going to punch this into Mathematica or Wolfram. So I'm going to first simplify it, and then I'll solve for finding the roots. It's a big mess here. 1 minus lambda. I'll just use x. And then brackets minus 5 minus lambda times 1 minus lambda plus 9. So that's the first term. I have a minus 3, parentheses. I got a negative 3 times 1 minus lambda plus 9. And then I have another plus 3 times, and then I have a minus 9 minus 3 times minus 5 minus lambda. Okay. Parentheses, balance, simplify. Okay, let's see what happens. So here's a nice factored form of this, which means we can have the solutions already for us, so that's good. You got x plus 2 squared, and then x minus 1, or 1 minus x. Okay, so x minus, forgot. I should just copy it. So whenever I do something in Mathematica or Wolfram, I should just copy it. So this is our polynomial, which means I don't have to ask Wolfram to find the roots for me. I'm going to have x equals 1, and then x equals negative 2. And this one has algebraic multiplicity of 2, because it happens twice. Okay. So I only have 2 eigenvalues, but one of them has multiplicity 2. So I'm hoping that when I find the eigenvectors, I need 3 linearly independent eigenvectors. So I'm hoping that when I put 2 in, or negative 2, I hope to get 2 eigenvectors out of that. Let's see if that's actually going to happen. So we find the eigenvalues, step 2. Find E vectors. They're hopefully linearly independent. So let's go and let's do 1 first. Lambda is equal to 1. So I need to go back to my a minus lambda I and put 1 in. So pretend that lambda is equal to 1. And what do we get? We get 1 minus 1 is 0. 3, 3, minus 3. Minus 5 minus 1 is negative 6. And then 3, 3, 1 minus 1 is 0. All right, so I need to find the solutions for this. I may want to do a row swap. Maybe I'll row swap the first and the third one. So I got 3, 3, 0, minus 3, minus 6, minus 3, and 0, 3, 3. And then maybe I'll multiply the first one by 1, I guess, and just add it to row 2. So I got 3, 3, 0, and this is going to be 0. Yeah, of course. Add. So this is negative 3 and negative 3. And then you can see that the second and third rows are essentially the same. So you can just knock it out. So we have a free variable at x3. So x2 is going to be negative x3. X1 is going to be equal to negative x2, which is equal to negative x3. So that's positive x3, isn't it? So x1 is equal to x3. Okay. So here we have for our eigenspace for lambda 1 is equal to 1, then our v1 vector is going to be, just take the x3s out. So I have a positive x3 and negative x3 and positive x3. So the eigenvector for this should be 1, negative 1, 1. Is that correct? All right. So let's box this and keep that for later. And Chris has a question. Yeah. Yeah. So for lambda is equal to 1, you span a one-dimensional space in R3. All right. So our only other eigenvalue is negative 2, and I'm hoping that we will actually get 2 linearly independent vectors out of this. So let's see if that actually works out. So lambda is equal to negative 2. Our matrix is going to look like our matrix is going to look like 1 minus negative 2. So that's a 3. 3. I have a negative 3. Minus 5 minus negative 2. Minus 5 plus 2 minus 3. And then I have a 3, 3, and then I have a 1 minus negative 2. 1 minus, that's going to be 3 again. So we got a thing full of 3s here. So basically, if you row reduce this, you're going to get a row of the same numbers and then zeros for the other 2 rows. What does that mean? That means you have 2 free variables, which is what we were looking for. X2, X3 are both free, and then our X1 is going to be minus X2 minus X3. So how are we going to write that? I think we're going to write it like our X is equal to, well, let me write it carefully here. I think this is how you would write it, right? So x3 is free, x2 is free, and x1 is equal to negative x2 minus x3. So if we break this up to 2 vectors, my x2 is going to get multiplied with a negative 1, a positive 1, and a 0. And my x3 is going to get multiplied by negative 1, 0, and positive 1. So just by inspection, we can tell that these 2 vectors are linearly independent. They're not multiples of each other. And so now we have 2 vectors associated with this eigenvalue. So the eigenspace here is going to be actually spanned by 2 vectors. So V2, I'll call it V2 since we have a V1 up there, is equal to minus 1, 1, 0, and V3 is equal to minus 1, 0, 1. So this eigenspace for this is going to span a plane. All right, now a part that we really want is to figure out our D and our P. So your D vector, oh wait, they want to form the P matrix first. So let's follow the step-by-step process. Step 3, form your P matrix. So your P matrix would just have these V1, V2, V3 as column vectors. So P is equal to V1 is 1 minus 1, 1. V2 is minus 1, 1, 0. And V3 is minus 1, 0, 1. They look awfully close to being linearly dependent, but I don't think they are. Yeah. Yeah. Sure. Uh-huh. All right. And then our D is going to be equal to, I guess I should have done the columns. So the column will have, well, the diagonal will have the eigenvalues. So this is going to match with your eigenvalue of 1, and then these two matrices will match the eigenvalue of -2. So I will now go into Octave or MATLAB. Let's try Octave. Yeah. Yeah. I don't think it matters, because if you switch the columns, as long as you're consistent with the P, then it should be okay. And I think we should try that out. So let's see. Let's say we have, sorry for people that are copying, x1 equals 1, x2 equals -2, and x3 equals -2. It's the same thing. I guess we don't need x3. So those are my eigenvalues, my eigenvectors, v1. What was it again? 1, -1, 1. So 1, -1, 1. Oh, come on. 1, -1, 1. And then my v2 vector is -1, 1, 0. Let's put a bracket around that. And then my v3 is equal to -1, 0, +1. All right. So according to this, my p vector, or my p matrix, is made out of v1, v2, v3. And then I have my inverse of that. It looks like it's a pretty nice inverse. There's no fractions or weird numbers like that. And I need to make a diagonal. I think I can do a diag. X1, X2, X2. Let's see if this will come up to be my diagonal matrix. Nope. Okay, I don't know how to do a diagonal matrix. So let's just call the diagonal matrix what is it? X1, 0, 0, 0, X2, 0, and 0, 0, X3, X2. There it goes. So this is my diagonal matrix, and my P inverse and my P are set. And so if I multiply P times the diagonal matrix D times the inverse of P, I should get my original matrix. Is that is that? Oh, is that the same? -1, 3, 3. Okay, so it did work. We found it, and so good. All right. So we have the process. We have a couple of simple examples. Oh, by the way, some of those questions, if we switch the order of the diagonal and the P matrix, it should still be okay, right? So let's take a look at switching, let's say P2, and let's say we switch the order and put the, where do you want to put the V1 vector, in the middle or in the end? In the middle. So V2, V1, V3. So if we switch the order and put V2 in the middle, then we would create our diagonal. Let's call this D2 equals -2, 0, 0. And then the middle one is 1. And then the last one is going to be -2. So we have to switch the order of our diagonal as well, right? And so if we do the P2 times D2 times P2 inverse, we should still get the same matrix that we had. Okay? All right. Any questions? Yeah. Then it's probably not diagonalizable. Yeah. Not diagonalizable. A question? You have a question? No. All right. Let's put a whole bunch of, just a couple of more theorems. So if you have n distinct eigenvalues, it's diagonalizable. Our example, we had 2 distinct eigenvalues and one of them was repeating. So when you have something like that, it gets kind of sketchy if it's going to be if it's going to be diagonalizable. In our case, it turned out that it did work, but in some cases it might not work. But if you have distinct eigenvalues, then it's automatically going to be diagonalizable. Theorem 7, if you have a set of eigenvalues 1 through p, right? So will probably be a little bit less than the dimension. So this is kind of like our example. For each k between 1 and p, the dimension of eigenspace is less than or equal to the multiplicity of the eigenvalue. So this dimension of the eigenspace that they're talking about is the number of linearly independent eigenvalues or eigenvectors for each eigenvalue. And sometimes that's called a geometric multiplicity. And they don't define it here that way, but that's what it is. If A is diagonalizable, then, or if and only if, the sum of the dimensions of the eigenspace is equal to the multiplicities. So that means the characteristic polynomials factors completely, and the dimensions of each eigenspace is equal to the multiplicity, algebraic multiplicity. And then the last one, if it's diagonalizable, then BK is a basis for the eigenspace corresponding to each eigenvalue. And then, this is what Brian had asked about earlier, those column vectors that we have, those linearly independent column vectors for P that we created from the eigenvectors, they actually would form a new set of basis for your Rn or R3 in our case. Okay? All right. The next section moves into this idea of basis stuff. So let's maybe pause on this for a minute, and I want to backtrack to in terms of finding an application for these eigenvalues and eigenvectors. I found one that was kind of interesting, but for that we need to backtrack and find some definitions and information from section 4.9. That's one of the sections that we skipped. So we don't need everything from there. We just need some of the basics. And let's talk about Markov chains for a little bit. And had we gone over 4.9 before going over this, we would think it was kind of interesting. But after going through eigenvalues and eigenvectors, we're going to see something immediate from one of the results from Markov chains. So let's state a couple of definitions here. One, a probability vector is a vector whose elements are all add up to 1. Each element is a probability. And if you know anything about probability, probability is always positive. It's always a number between 0 and 1. So a probability vector is a vector whose components add up to 1. A stochastic matrix is a matrix whose columns are made up of these probability vectors. So if you take a bunch of probability vectors, put them up together and to make a square matrix, then you have what's called a stochastic matrix. That's a matrix that they use a lot in statistics and probability. And so Markov chain is a collection of vectors that gets applied to a stochastic matrix. So you have x sub 0, you apply it to the matrix, you're going to get a new vector. You take that new vector, apply it to the matrix, you get another new vector. You take that new vector, apply it to the matrix, you get another new vector. And that collection of vectors that you're going to get is called a Markov chain. So a Markov chain is more compactly defined as they call it a difference equation here. So to get the next element in the chain, you have to take the last element in the chain and apply it to the matrix P, stochastic matrix. Yeah. Yeah, so x0 would just be an initial starting point matrix, or vector, initial starting point vector, probability vector. And then you would get x1 by applying that vector to a stochastic matrix. By applying, I mean matrix multiplication. So you're going to get x1 by saying p times x naught. P being the stochastic matrix, yeah. Mm-hmm. It will give you the next vector in the chain, x1. And then you take that, apply that to the matrix again, and then you're going to get the next vector in the chain. And then you keep doing that, and then you keep getting more and more vectors. Okay? Now, what's interesting about this with stochastic matrices is that sometimes, not all the time, but sometimes, um, sometimes you keep doing this application to the chain, and eventually the chain settles down to a set of numbers that's not going to change anymore, right? Yes. Equilibrium. So you apply this matrix, you apply this vector to the matrix, you get another vector. You keep doing that, and then maybe at some point you apply it, and then your numbers look like they're the same. And then you apply it again, and your numbers look like they're the same. And then eventually it'll be the same. Stochastic matrix. No, not the nth power of the matrix, but the vector that you're applying when you apply it to the matrix will be the same vector. Okay? Not okay? All right, well, let's see if we could do an example. So the whole motivation behind throwing this at you is because if you look at this equation, what does this look like? Oh, here, let me change this. Which is not quite. I mean, we'll get there, but what's 1? 1 is a number. It's not a matrix. What's 1? 1 is an eigenvalue. And then Q, the steady state vector, happens to be an eigenvector. Right? So it'd be AV lambda V, except V is Q, and then lambda is equal to 1. Okay? Now, this is used in a lot of applications, but one cool application I saw this in was called the Pagerank Algorithm. Anybody familiar with the Pagerank Algorithm? So the Pagerank Algorithm is some complicated algorithm. It's not that complicated, really. It's an algorithm that they use to for Google searches. So what they do is they take a whole bunch of pages, and then they figure out what the popular pages are by how many links go into it, and then they rank your pages that way. So when you do a Google search, you know, I used to come up on top in my Google searches, but it's changed in a while because I haven't used my website. So when you do a Google search, right, Google has to try to figure out where your search is going to go or what's going to be on top, and that whatever goes on top kind of depends on yeah, it depends on how many other pages link to your page. And so that's how that is called a Google rank page. And so I used to be in like the top 3, but now I've gone down. You know what else is in the first page? Right, my professors. No. No. I know what it says. He's too hard. Wah, wah, wah. What? Some do. So what we're going to do is we're going to, I'm not going to give you much detail, but I'll just do a quick example, and we'll do a World Wide Web of 4 pages. We'll just, because otherwise we could be here for a long time. Yeah. So back in the old days, we had a simpler, back in simpler times, we had a web page. Well, we had the web only has a few, a small amount of pages. And so let's take this for example. Let's say we have 4 pages, and the arrows describe linking to other pages. So if I go to page number 1, there's a link in page 1 to go to page 3 and page 2. And then if I go to page 2, there's a link in page 2 that would go to page 3 and page 4. And if I go to page 4, there's a link that goes to page 1 and page 3. Okay, so that's the idea. So I don't know if 1, 2, 3, 4 would be good. Let's change this to A, B. I can't see B. Oh, that's B. And this is D. And this is C. A, B, C, D. Okay. So in page A, I'm going to link to itself. I don't have a link to itself, so I'm going to put 0 there. And then I'm going to link to B once, to C once. Do I link to D? Yeah, I link to D. Is this a probability vector? No, so let's make it into a probability vector. How would you make this into a probability vector? So divide by 3, right? There's 3 components. So 0, 1/3, 1/3, 1/3. So that's my probability vector for A. And then I can construct a probability vector for B, C, and D. So I'm going to skip over that and just say my matrix, let's call it P. This is my stochastic matrix, is going to be 0, 1/3, 1/3, 1/3. And then my probability matrix for B, B goes to C and D, right? And nowhere else. So what should my vector look like? 0, 0, 1/2, 1/2. It's 1, 1, right? It goes to C and D, but then I want to make it into a probability vector. My C goes to A, nowhere else. So what should it be? So A is the first one, right? So 1, 0, 0, 0, and then D goes to where and where and where? So it goes to A and C. So that's my P vector, right? So now I want to start off with an initial state. And initial state, what I'm going to do is I want to apply this initial state to the probability vector to say if somebody was randomly choosing a web page and then they click from wherever web page they are, they click on another web page that connects them, then where would they end up? Well, what's the probability that they would end up in page A, B, C, or D? And to start off with, generally you give it an even chance for everybody to say everybody has the same ranking. Okay, so you would apply this to the P matrix to get X1, and then you would apply X1 to the P matrix to get X2, etc. Then eventually, if this thing settles down, then it would be considered a steady state. Okay, so the other thing to do is to find the eigenvalues of this and see one of the eigenvalues is equal to 1 and find the corresponding eigenvector. Okay, So what I'm going to do is I'm going to make a recording of the rest of this information, maybe start from scratch, and then I'll post it up online. You guys will have a couple of quizzes to do. 3. So one of them would be due on Monday after spring break. 2 of them will be due Monday after spring break, and one of them will do Wednesday after spring break. All right, have a good spring break.